Have you ever looked at a massive cargo plane and a tiny fighter jet and wondered, how can they both be airplanes? Well, it's not just about their mission. It's about a whole series of invisible compromises, a balancing act of physics that defines what a plane can do and, more importantly, what it can't. Today, we're going to dive into the physics of flight performance to really understand these fascinating trade-offs. So let's just start with the biggest question of all. Why can't we build one plane to rule them all? One that's super fast, can carry a ton of weight, and land on a tiny little runway? Well, the simple answer is that the laws of physics demand a compromise. Every single aircraft is a unique solution to a specific problem. And that brings us to what pilots and engineers call the performance puzzle. Honestly, thinking of it as a balancing act is the perfect analogy. You can't just keep adding cool features to one side without taking something away from the other. Performance isn't just one thing. It's a whole collection of different goals that are often fighting against each other. So when we say performance, what are we really talking about? In aviation, it's definitely not just about speed. Performance is all about how well a plane can do the specific job it was built for. For a crop duster, high performance means being incredibly agile down low. But for a transatlantic airliner, performance means being super fuel efficient for thousands of miles. Two totally different goals. This right here, this lays out those classic trade-offs perfectly. You want to fly incredibly fast? Okay, but you're probably going to sacrifice some fuel economy and need a great big runway. You want to carry a massive payload? For sure, but all that weight is going to hurt your range and how fast you can climb. Every plane you've ever seen is a specific answer to this puzzle. All right, so let's see how these trade-offs actually work in real time, starting with the very first phase of any flight, getting airborne. The climb isn't just a matter of yanking back on the stick and pointing the nose to the sky. No, it's a really precise game of managing energy. At its core, climbing is just swapping one kind of energy for another. On the runway, the plane builds up a ton of kinetic energy. That's the energy of pure speed. Then, once it's in the air, the pilot starts converting that speed into potential energy, which is just the stored energy you have because of your altitude. It's kind of like a skateboarder hitting a ramp. They trade all their forward momentum for height. Same idea, just with wings. So you're rolling down the runway, you lift off, now what? The question for the pilot isn't just how do I go up? It's what specific problem am I solving with this climb? Because depending on what's in front of you, there are two very different and very important ways to climb. Let's say there's a huge line of trees or some power lines at the end of the runway. The problem is an obstacle. In that case, the pilot needs the best angle of climb, or AOC. This gives you the steepest possible climb path. You're gaining the most altitude while covering the least amount of ground. It's your get over that thing right now climb. But what if it's just clear blue sky ahead? No obstacles. Now the goal is just to get up to your efficient cruising altitude as fast as you can. That's when you use the best rate of climb, or ROC. Think of this as the express elevator. You're gaining the most feet per minute, even if it means covering a bit more ground to get there. And this chart just makes it crystal clear. Look at that. Using max AOC, the plane gains 1,000 feet over just 3,000 feet of ground distance. Perfect for clearing those trees. But switch over to max ROC, you actually gain more altitude in the same time, 1,500 feet, but it takes you twice the horizontal distance to do it. See? The best climb is all about the mission. Okay, so we've climbed up to altitude. The seatbelt sign is off. Now we're settling in for the cruise. Up here, the name of the game changes from raw power to pure efficiency. And to talk about that, we have to understand two key ideas that people mix up all the time: range and endurance. The distinction is actually pretty simple, but it's critical. Range is all about distance. How many miles can this thing fly? Endurance, on the other hand, is all about time. How many hours can it stay in the air? Think about it. A surveillance drone needs maximum endurance to loiter over a target, while a passenger jet needs maximum range to cross an ocean. So how does a pilot actually get one or the other? Well, to get maximum range, you're looking for an aerodynamic sweet spot called L over D max. It's the point where you get the most possible lift for the least amount of drag. It's peak efficiency. But for maximum endurance, the goal is a little different. You're just trying to find the speed that lets you use the absolute minimum amount of power to stay level, so you're sipping fuel as slowly as possible. And here's where it gets really tricky. This is not a set it and forget it kind of thing. As a plane flies for hours and burns off thousands of pounds of fuel, it gets lighter. And that perfect sweet spot for maximum range it actually changes. It's a moving target. So long-haul pilots are constantly making tiny adjustments to stay in that peak efficiency zone. So we've climbed, we've cruised, but now it's time for the most challenging part of any flight, the approach and landing. And this is where we run into one of the most counterintuitive, absolutely critical, and just plain weird concepts in all of flying. It's a strange place called the region of reversed command. Let me ask you a quick question. To fly slower, you reduce power, right? It's just common sense. In your car, you lift your foot off the gas to slow down. But in an airplane, when you're getting slow for landing, the answer is surprisingly, no, not always. And that's the paradox. This region of reverse command is a phase of low-speed flight where everything feels backwards. You're flying so slow that to get even slower, without falling out of the sky, you actually have to add engine power. Your instincts are telling you one thing, and the physics is telling you the exact opposite. So what on earth is happening here? Well, it's all about a nasty little thing called induced drag. You can think of it as the energy cost of creating lift. At high speeds, it's no big deal, but as you slow down and have to pitch the nose higher and higher to stay flying, this induced drag just skyrockets. It's like a giant invisible anchor is thrown out the back, and you need more and more power just to fight it. And believe me, this isn't just a textbook theory, it's a real and present danger. Picture a pilot taking off from a soft grassy field. They pull back too early, trying to force the plane into the air before it has enough speed. Suddenly, they're on the wrong side of that power curve, deep in the region of reversed command. The drag is immense, and even with the engine at full blast, the plane just won't climb. The only way out is to do the scariest thing imaginable close to the ground, push the nose down to gain speed, even if it means losing precious altitude. And that is why every single pilot has to master this concept. Understanding this backward-feeling region is the absolute key to safe, controlled landings and avoiding disaster during the most critical parts of any flight. It's a perfect example of how knowing the physics isn't just academic, it's about survival. You know, this quote here really brings it all full circle. It's just a formal way of saying that every single plane is a carefully calculated compromise. The manufacturer is playing that balancing act from day one, matching the shape of the wings and the body with the power of the engines to make a machine that's really, really good at its one specific job. So let's bring it in for a landing with the three big ideas. First, no plane can do it all. Every design is a series of trade-offs. Second, climbing is all about swapping energy, and pilots have to choose between a steep angle of climb for obstacles and a fast rate of climb for efficiency. And finally, the big one. Remember that when you're slow, the rules get weird. You might just need more power to fly slower. And that leaves us with one final thing to think about. As we design the next generation of aircraft, electric jets, supersonic transports, urban air taxis, how will these same fundamental, unchangeable trade-offs shape what's possible? The physics doesn't change, but the solutions engineers come up with, well, that's going to be really fun to watch.